All right, I think it's time to get started. Welcome, everyone, to today's seminar. Michael Kinyon from the University of Denver will speak about conjugacy in semigroups. Please, Michael.
Okay, well, first of all, thank you very much to Peter for the invitation. I'm going to be painting with a rather big brush here. I'm just going to be giving an overview and survey of issues surrounding conjugacy in semigroups, mostly focusing on what in the world would you even mean by conjugacy in a semigroup. Okay, actually, I need to make one minor adjustment here to my am I frozen?
Video is frozen. I hear you clearly.
Okay, well, that's something. I could just
Can you move your mouse? Okay.
Yeah,
The slides are fine. It's just that your face is frozen.
in a rather awkward position, I can see. Well, that's all right. You don't want to look at me anyway, so that's fine. Well, I seem to be back. Anyway, never mind. It's not important. Okay, as I was saying, I'm going to be painting with a rather big brush here, just kind of an overview of issues surrounding conjugacy in semigroups. Now, before we actually do that, let me start by, first of all, casting blame on all my co-authors. So any mistakes in what I'm about to discuss are, of course, due to them. This is not all one single paper. This is a collection of projects where the intersection of all the co-authors happens to be me. All right, so let me first, just to sort of set the tone, start with some stuff that is sufficiently basic that I run the risk of insulting your intelligence, but I simply want to do this to give a sense of where we're heading. Let's talk about conjugacy in groups. We won't say too much other than the basics. So what conjugacy in groups means is just that two elements are conjugate if, when we multiply by some other group element on one side and the inverse of that element on the other side, for one, we obtain the other one. And this is, of course, an equivalence relation on groups, but it's also a little bit more than that because the equivalence classes are actually orbits of a permutation action. Now, for each element of the group, the corresponding mapping conjugation by that element is an automorphism. And I'm just going to be consistent. I hope I'm consistent throughout the slides. I'll use phi sub g for this map. This is the part where all students, of course, bemoan the fact that for some reason conjugation doesn't have a standard symbol. The set of all the inner automorphisms, like these are, is, of course, a subgroup of the full automorphism group and is usually called the inner automorphism group. And finally, the mapping that sends the group to the corresponding inner automorphism is a surjective homomorphism whose kernel is precisely the center. So far, so good. This is all just undergraduate group theory. Nothing new here. But let's now think about how we would move on to the case of semigroups. Now, before we do this, before we start talking about conjugacy in arbitrary semigroups, I'd like to start by talking about inverse semigroups, as I mentioned in the abstract. Excuse me one second. There we go. So what is an inverse semigroup? Well, an inverse semigroup is a semigroup such that each element has an inverse, but inverse is used in a different sense than is typically used in group theory. It's used in a broader sense, the way semigroup theorists tend to use it. An inverse is an element such that if you stick it in the middle between the original element, you get that back. and also the other way around, as the two equations on the slide indicate. And so an inverse semigroup is one in which every element has a unique such thing, or an alternative description of them, which is equivalent, is that every element has some inverse, and the set of all the idempotents is actually commutative, actually forms a semi-lattice. And I'll stick with the traditional symbol for the set of all idempotents here, which is the first letter in the word idempotent, namely the letter E. Okay. A standard example of an inverse semigroup is the symmetric inverse monoid. If you're given any set, then you consider the set consisting of all the partial bijections between subsets of that set. And under composition of partial mappings, this is an inverse semigroup. And it's the sort of the exemplar for a variety of reasons, not the least of which is that there is a generalization of Cayley's theorem, which is usually called the Wagner-Preston theorem, or sometimes the other way around, Preston-Wagner. And it says that every inverse semigroup actually embeds into the symmetric inverse monoid on the underlying set of the semigroup as an inverse subsemigroup. So this is precisely a generalization of Cayley's theorem. It probably has some categorical interpretation in terms of the Oneida lemma, but I have no idea what that would be. Anyway, now I'm going to a quick notation convention, which I'm going to be using throughout the talk. I could have just at the outset of the talk said we're going to be talking about monoids, but the truth is that there are situations where it's better just to allow your semigroup not to necessarily have an identity element. In that case, we use this notation. When you stick a superscript 1 on the underlying symbol for the semigroup, that is either the underlying semigroup if it already was a monoid, otherwise you adjoin a new identity element. Okay, so I'll be using this throughout. S1 it means this to a semigroup theorist. It's not, for example, the symbol for the unit circle in the complex plane. Okay, so let's take the definition of conjugacy in groups and just naively replicate it in inverse semigroups, because after all, there's a natural notion of inverse in this setting, and let's just see what happens. So we'll say that two elements are naturally conjugate, naturally meaning from an inverse semigroup point of view. If there is some other element in S1 that conjugates each to the other, and also with the inverse. This is an equivalence relation. Now, the reason you, unlike the group case, you do have to include both equations here. Otherwise, it is not necessarily symmetric. And although I don't have an axiomatic characterization of what exactly conjugacy in a semigroup should be, at the very least, it should be an equivalence relation. The transitivity follows from an identity, the anti-automorphic inverse property, which holds in groups and also holds in inverse semigroups as well. So now the question arises, how much of what we know for groups, so all the things that I mentioned on the first couple of slides, inner automorphisms and so on, how much of that can we salvage in this more general setting? Okay, so the answer, interestingly enough, was worked out almost entirely by a paper by Preston, who was one of the founders, if you like, of inverse semigroup theory, along with Wagner. This paper, I wouldn't say that it was published obscurely. It certainly was not, but it's one of his less cited papers. I've only found 2 subsequent papers that actually cite it. It took a while to even find those. And they only cite small parts of Preston's paper that actually don't have much to do with what I'm going to be talking about. And their matters sat for a while, and then the theory was all worked out again independently by Melnik in the Russian literature. and then later by Mario Petrich in a couple of papers where he was developing the theory of conjugate extensions, normal and conjugate extensions of inverse semigroups. And Preston's paper isn't cited in either Melnick's paper or Petrich's two papers. However, some of you may be familiar with Mario Petrich's giant book on inverse semigroups. It's, if I remember correctly, about 684 pages, which is, it's about as encyclopedic as it gets. And apparently in the writing of that book, he became aware of both Melnick and Preston's work, and he cited them explicitly in the main text. So much for the history. What is the answer? Okay, so it goes like this. Just a moment, I need to make a screen adjustment because you're all in the way there. Okay, there we go. Okay, so, excuse me. Suppose we have an inverse semigroup, fix an element in S1. And let's consider the two idempotents, GG inverse and G inverse G. You can think of these as being respectively domains and ranges for corresponding elements of the symmetric inverse monoid, for example. And let's consider the local subsemigroups, which are in fact inverse subsemigroups, ESE, and that's supposed to say FSF. I'm sorry, that's a typo. Then what we do is we define a mapping with domain ESE just by conjugation by G, in the sense that we talked about before, G inverse XG for any X in ESE. And you'll notice I'm following the standard convention in semigroup theory that mappings, especially local bijections and or partial bijections and things like that, are acting on the right of their arguments. Then Preston showed a number of things. He showed, first of all, the image under this map is actually FSF, that the other local subsemigroup. And the mapping, in fact, between the two is an isomorphism of inverse semigroups. And then furthermore, these things compose exactly the way that you hope they would. So we call these phees partial inner automorphisms. So they're inner because they're constructed in the same way as in the group case, and partial because they're not totally defined mappings on S. And Preston also showed that he used different notation, but he showed that the partial inner automorphisms form an inverse submonoid of the symmetric inverse monoid. The mapping that sends S1 to the corresponding partial inner automorphism is a surjective homomorphism. And also a useful fact is that this mapping is idempotent separating. If you have distinct idempotents, their images are in fact distinct points. Now, so all that's left here is to describe the kernel of this homomorphism uppercase phi. And I mean kernel in the sense of kernel relation, meaning kernel congruence. So let's talk for a moment about congruences and inverse semigroups. The congruence theory for inverse semigroups is much nicer than for the rest of semigroup theory, with the obvious exception of groups, because a congruence on an inverse semigroup is entirely determined by two pieces of data. The first is the so-called kernel of the congruence. Yes, kernel is one of those, as you all know, it's one of those much overused words in mathematics. And it's in fact used in at least 3 distinct ways in semigroup theory, unfortunately. This is one of them. The kernel consists of the union of all the congruence classes which contain idempotents. And then there is the other piece of the puzzle, which is the so-called trace of the congruence. And that's the restriction of the congruence to the idempotents. And the congruence is entirely determined by these two pieces of data. They satisfy some compatibility conditions, and it's possible to completely reconstruct a congruence given this data. So the kernel here, which I've called N, is the natural generalization of what a normal subgroup should be. It's known as a normal inverse subsemigroup. It's closed. It's a subsemigroup. It's closed under taking inverses. It contains all the idempotents, and it is self-conjugate. It's closed under. It's conjugating the whole subset. Stays inside the subset. Now, if you have a idempotent separating congruence, meaning exactly what it sounds like, the congruence, the idempotents separate themselves into distinct congruence classes, then that means that the trace of the congruence is in fact the equality relation, in which case the kernel still tells the whole story. Okay, so what's left is then to describe the kernel of phi. And there are several ways to describe it, but here's a relatively succinct one. Okay, so for an inverse subsemigroup, let's let Z of S or Z of S, if you're Canadian or British, be the set of all elements that sort of commute with everything in the semigroup. But you notice that the commuting is defined in sort of a strange way. So it's AX, and then on the other side is the idempotent A inverse A, and that's equal to A inverse AA inverse, the other idempotent XA. Okay, so this has been called different things. Melnyk referred to it as the quasi-center. Petrich called it the meta-center. It's a normal inverse subsemigroup, and it contains the so-called classical center. The classical center being just the set of elements that commute with everything. Petrich showed, and I think Melnyk did too, although I'm not 100% sure, that the kernel of our homomorphism phi is precisely this Z of S. Now, I'm using kernel in the sense of the previous slide, the union of the congruence classes of idempotents. And excuse me. And phi, in fact, is injective if and only if our Z of S here is exactly the semilattice of idempotents. Okay, so much for that story. As I said, this is mostly due to Preston, except for terminology and some notation. Now, when David Stanovsky and I, several years ago, set ourselves the task of determining, well, a lot of you know him and you know he's a universal algebraist. I'm not a universal algebraist, but he suggested the task of determining what is the universal algebra center of an inverse semigroup, that is the maximal central congruence. And this is why in the previous slide I referred to the so-called classical center, because I tend to think of the universal algebra center as being the true center. But that just here on the slide, that just reveals the fact that at heart, I'm basically a quasi-group theorist. Okay, so we weren't aware of all of this work that had been done, even though it's all worked out. For example, in Petrich's book has the well, let's just say it has the distinction of being one of those books that many people refer to and very few people read. And I confess that I was guilty of that at this point. Anyway, this is one of the main theorems that David and I came up with. This paper is currently under review and there's a copy of it sitting on the archive. So in an inverse semigroup, the Abelian congruences are those where the kernel is a commutative inverse subsemigroup, and the trace is equality. And the central congruences are those that with kernel that sitting inside Z of S and have trace equality. And so as a consequence, the center of an inverse semigroup is the congruence, which is actually determined by our friend Z of S and the equality relation on the semilattice. As an example, and this shouldn't come as a surprise if you think about symmetric groups, based on this, it's easy to see that the symmetric inverse monoid, if your underlying set is sufficiently large, has trivial center. I will say, by the way, with regard to all of this, we don't have a very complete description of what commutators in the universal algebra sense of commutator, what they look like in inverse semigroups. I mean, we sort of know, of course, in the same sense that you know about any commutator in any algebra, but I mean a more specific hands-on description that's specific to inverse semigroups. But nevertheless, we were able to characterize the Abelian and central congruences, and for our purposes, that was enough. Now, this next result from that same paper might be a little bit disappointing if you're looking to generalize the theories of nilpotence or solvability, and again, I mean those in the universal algebra sense, to inverse semigroups, and that is that an inverse semigroup is nilpotent or solvable if and only if it's in fact a nilpotent group. And fairly recently, at least I think it was recently, Radovitz and Mudrinsky gave a completely different proof of this using higher commutator theory. So they approached rather than doing it from a semigroup theoretic point of view, which is how David and I approached it, they came at it starting with super nilpotence and the concepts surrounding that. All right. So let's move on to conjugacy in some other types of semigroups. In fact, in general semigroups. So one of the first things that you may have thought of when I wrote down the equation G inverse AG equals B is there's an easy way of getting rid of the inverses. Just multiply both sides on the left by G, and you get the defining equation AG equals GB. And in groups, of course, that's a perfectly reasonable way of defining conjugation instead of G inverse AG equals B. So if we symmetrize this, then we obtain a notion of conjugacy in arbitrary semigroups. This is again an equivalence relation, and another requirement that you might ask for any reasonable notion of conjugacy, besides the fact that it should be an equivalence relation, is that when you're talking about groups, your notion should agree with the classical one for groups. So this is we're denoting this by tilde sub O. Since there are several conjugacies here, you need some kind of way of keeping track of them. It's not actually clear who was the first one. This is an obvious definition, but it isn't really clear who was the first person who thought of this as a conjugacy, as opposed to just something else, some relation. It's explicitly called a conjugacy in Lallemont's book, Semigroups and Combinatorial Applications from 1979. But it could certainly some of the theorems that he proves about it predate him, and perhaps thinking of it as a conjugacy does too. The reason we call it tilde sub O is for Otto, who used this to study some types of rewriting systems. Used it quite extensively, in fact. Okay, here's a different notion of conjugacy. This one is usually called primary conjugacy, or just P conjugacy. And it's motivated by the following observation in groups here at the top of the slide. So if we start with group conjugation, again, G inverse AG equals B, then let's make some change of notation. Let's let U be AG and V be G inverse. Then you'll notice that U times V is A and V times U is B. Conversely, if you have a pair of elements U and V that satisfy that, UV is A and VU is B, then you can undo all this to get conjugacy in the way it's usually defined. Okay, so that means that we have yet another characterization in groups of conjugacy, and it's one which is inverse free, and so we can use it to define a notion of conjugacy in any semigroup. So we start with tilde sub p, and that's just exactly what I said. There are a couple of elements in S1, so that the pair of conjugate elements can be expressed as UV and VU respectively. Now, this is not in general a transitive relation, as you can pretty easily guess. So to really get a notion of conjugacy, we take its transitive closure. Okay, and this transitive closure is usually called primary conjugacy. The tilde p is still singled out on its own as an interesting relation just because it's convenient to do so. Okay, so how are these things related? And what are some things that one can say? Well, first of all, our tilde sub O conjugacy is a rather weak one. So for instance, if your semigroup actually has a 0, then autoconjugacy is in fact the universal relation, which means it's completely useless. So in any semigroup with 0, and many semigroups do have zeros, in fact, asymptotically, finite semigroups, it's believed that the ratio of semigroups with a 0 to all semigroups approaches 1 as the orders of the semigroups get bigger. This is not proven, but this is a general feeling. Now, the three notions that we've been talking about, specifically the two of primary conjugacy and autoconjugacy, are related in this way. One of them, they're contained upward, and these are all strict inclusions, except in special classes of semigroups, they might coincide. So, for example, Linden and Schoessenberger proved that in free monoids, all of them coincide. Now, they didn't, in their old paper, they didn't think of a tilde sub O as being a notion of conjugacy. Rather, they just proved something that said that if it holds, then the other one, tilde P, which they were thinking of as conjugacy, also holds. As another case I can mention, in bands, which are idempotent semigroups, tilde P is transitive. So tilde P and tilde P star coincide, but they don't necessarily coincide with autoconjugacy. So anyway, this is how these things are generally nested. Now I'd like to do a very interesting aside, which I only became aware of fairly recently. And that is that the whole idea behind primary conjugacy was independently discovered in the dynamical systems literature. I'm going to ignore some of the details here, not because I don't understand them, but because they would take too long to describe. But here's the idea. There's a type of dynamical system which is called a shift, or sometimes subshift, of finite type. It's not too important what it is, but what they are for us, for this audience, but they are in a one-to-one correspondence with square matrices with non-negative integer entries. And the relation that we're calling primary conjugacy on these matrices is exactly what in dynamical systems language is called strong shift equivalence. And Williams proved actually that two non-negative integer matrices are strong shift equivalent if and only if their corresponding shifts, the dynamical systems themselves, are topologically conjugate. And this is conjugate in a sense that basically you can think of it as being the dynamical systems version of what isomorphic should mean. Topological conjugacy is not exactly like group theoretic conjugacy. It's really a homeomorphism between dynamical systems that intertwines the dynamics. So it's kind of interesting to me, and as far as I can tell by digging through the literature and asking my friends who in dynamical systems, as far as I can tell, this was entirely an independent development and was not based on any connection with the semigroup literature. Now it goes a little bit further, which is kind of interesting. So while I was actually preparing for this talk, I thought it would be fun to tell you about the dynamical systems connection. And as I was reading some of the literature to make sure I wasn't telling complete lies about everything, I'm not telling complete lies, I'm just telling partial lies. I noticed that Williams not only defined strong shift equivalence, the strong apparently has some meaning. There's a weaker notion, which is just known as shift equivalence. And matrices of non-negative integers are shift equivalent if there exist a couple of other matrices and a non-negative integer k such that these 4 equations in the display hold. Now, if you look at the first 2, those are exactly the conditions for autoconjugacy. And then the second 2, the ones for GH and HG, are these are additional constraints that are put on the conjugating matrices G and H. Now, shift equivalence, as far as I understand it, does not correspond to an equivalence relation on dynamical systems themselves. The main reason shift equivalence is of interest to dynamical systems people is because computationally it turns out to be easier to check. So if they, for instance, if they want to check if 2 dynamical systems are not strong shift equivalent, sometimes it's easier to check that they're not shift equivalent. Well, it's pretty clear that just messing around with symbols that you could play this game in semigroups. So let's define a brand new conjugacy in semigroups, and just see what it gets us. So here it is. We'll say that 2 elements of a semigroup are W conjugate, W for Williams here. If there exist corresponding elements of S1 and a non-negative integer or natural number, such that the 4 equations that were on the previous slide hold, this time in the general semigroup setting. Now, I am, having done my homework on this, I'm reasonably certain that this particular notion of conjugacy has never been seen in the semigroup literature. But of course, you don't want to just introduce notions of conjugacy at random. So a question is, does this actually mean anything, and is it interesting? It turns out the answer is yes, somewhat surprisingly. So first of all, how does it fit into the ones we've already talked about? It's actually between primary conjugacy and autoconjugacy. You can see immediately that it's that it implies autoconjugacy. For the other inclusion, that's not immediately obvious, although it's a little bit easier to see if you just work with tilde sub p, then you can see how to induct upward to get that inclusion. So here is a new result, which I actually proved yesterday while I was preparing for this talk. And it's based on the following. There is as yet another notion of conjugacy, this time for finite monoids, which comes from representation theory. So in a finite monoid, 2 elements are said to be character conjugate if for every irreducible character of the monoid. So what is an irreducible character? You take an irreducible representation over a complex valued vector space, and then a finite dimensional one, and then you take the trace of your representation matrices. So for every such representation, if the corresponding characters agree on the elements, that's called character conjugacy. And it's well known that for finite groups, this is equivalent to conjugacy. Now, this description of character conjugacy is actually not the definition that you can find in the semigroup literature. It's a characterization. This is the theorem that they prove. I'm taking it as a definition for simplicity in this talk. The actual definition is a little too technical for to get into. Well, here is the theorem which kind of surprised me. This notion of conjugacy that I just defined for you, which came from dynamical systems, and just translating dynamical systems stuff over to semigroup theory. it turns out, is exactly equivalent to character conjugacy in finite monoids. I was a little bit surprised to see that this is the case. It leads one to wonder about the connection between representations of representation theory for finite monoids, for example, or other types of monoids, and shifts of finite type in the dynamical systems sense. Unfortunately, I'm not enough of a dynamical systems person, which you should interpret to mean not at all, to have very much to say about that. Okay. And finally, I'd like to talk a little bit about what's so-called natural conjugacy. And this was defined a few years ago by Janusz Konieczny. And you may recall that we actually used that terminology before, and I'll explain why in a second. So here's what natural conjugacy looks like. Two elements are said to be naturally conjugate if there are conjugators, so that we have the auto-conjugacy conditions, AG is GB and BH is HA. And in addition to that, we have something that looks like classical conjugacy, and it would be if H and G were actually inverses of each other. Now here they're not assumed to be. Now this one actually, this is in some sense the strongest notion of conjugacy. And here's how it fits in with the other ones we mentioned. Now, I don't have, by the way, the impression that every notion of conjugacy that has been studied in the semigroup literature fits neatly into a line. That isn't true. There are other ones that don't fit in here. What I can say, though, is that in the hierarchy of conjugacies, autoconjugacy is always at the top, and natural conjugacy, at least of all the known notions of conjugacy, natural conjugacy is at the bottom. This is not to say that natural conjugacy is the least minimal conjugacy. That would, I mean, first of all, what would that even mean? And secondly, there's no evidence to suggest that anyway, other than the fact that it's just very well behaved. Okay. So here was why Konieczny called it natural conjugacy. It turns out that this notion that I just defined for you, which I did entirely without inverses, if you're in an inverse semigroup, it's equivalent to natural conjugacy as I defined it at the very beginning of the talk. So that is, you can replace the G and the H that were in the previous definition with just a G and its inverse, and have conjugacy in the naive expected sense in an inverse semigroup. And this is exactly the same as natural conjugacy in the broader sense. Konieczny originally proved this by appealing to the Wagner-Preston representation, but in fact, there's a direct equational proof that isn't very hard. It's also not very enlightening, so I'm not going to show you what it is, but it's pretty easy. Okay. So let me mention Green's relations. Now, if you've ever heard a semigroup theory talk before, you know that it's a requirement that there is at least one slide that talks about Green's relations. And sometimes they draw egg box pictures and other such things to illustrate these things. So even though I come originally from quasi-group theory, in order to continue to pretend to be a semigroup theorist, I have to show you this slide. So Green's equivalence relations, L, R, well, this is 4 out of the 5, L and R and D and H, are defined like this. So two elements are L related if the the left ideal that each one generates, the left ideals that they generate, two elements are R related if the right ideals coincide. The join of those are equivalence relations. The join of those equivalence relations is called D. And it turns out that as relations, L and R actually commute. So therefore, that's in fact the join. And then the other one is excuse me, is H, which is the intersection of L and R. There's also another one here which doesn't play a role that you may have run into if you've heard semigroup theory talks, which is J, and that's when the two-sided ideals generated by elements coincide. Okay. So why am I mentioning Green's relations? Well, like I said, for one thing, I have to, and for cultural reasons. But the other reason is because that natural conjugacy actually plays well with them, specifically with D. So unlike all the other notions of conjugacy, natural conjugacy sits inside D. That is, if you have two elements that are naturally conjugate, they are in fact D related. And in particular, there's a couple of conclusions that one can draw from this with just some slightly additional arguments. First of all, natural conjugacy is the best behaved conjugacy for semigroups that have a zero. Because if a semigroup has a zero, then the singleton containing that zero is a conjugacy class. And that's not true of any of the notions of conjugacy that are sitting above this. Another is that, sorry. Another fact is that if you restrict natural conjugacy to just the set of idempotents, it coincides with the D relation, in fact. Okay. So to kind of, what I want to do now is I want to kind of circle back. I'm actually very close to the end, as strange as it may seem, probably because I've been talking too fast. What I want to circle back to some of the concepts from the very beginning of the talk. And so to do that, let me talk about some different ways of defining naturally conjugate. So the top 4 equations in the 8 displayed equations here were the ones that I used as the definition, and I used that just because Konechny did in his original paper. But in fact, if those hold, then all 8 of these equations hold, and you can take different combinations of them to give different definitions of natural conjugacy. That is, various subsets of these equations imply all the rest of them. Well, you know, ordinarily that's just playing a game, and that wouldn't be very interesting. But there's actually one combination of these equations that makes a very nice axiomatization of natural conjugacy, and that's these 3. So 2 elements are in a semigroup are naturally conjugate if and only if for the G and H out of S1. The first condition is that GHA and AGH are both equal to A. So GH acts like an identity element when it's applied to just to A. And the second condition is that B is HAG. That's the one that sort of looks like a conjugation in the classical sense. Now, the way to think about this is think about that first condition as defining a domain, and the second condition as defining a transformation on that domain. So here's how we'll do that. So D for domain here, set D sub GH to be the set of all the elements that satisfy the first condition. So GHA is actually AGH. Now, it's not very difficult to show that this is in fact a subset, subsets. Obviously, it's a subset, sub-semigroup, excuse me, of your semigroup. And then we define the transformation using the second condition for naturally conjugate. So phi sub GH from the domain to the semigroup is just defined by H times A times G. Now, if this is looking a lot like what I was at the very beginning of the, excuse me, at the very beginning of the talk, that's deliberate. So here we go. Here's the theorem regarding these things. First of all, the phi sub GH that we just defined is actually an isomorphism of the domain determined by G and H onto the domain determined by H and G. And when I say isomorphism, I mean isomorphism of semigroups. And its inverse, in fact, is phi sub HG. In addition to that, these domains are unions of H classes. So that means that the domains themselves play well, excuse me, I'm terribly sorry. That means that the domains themselves play together well with the Green's H relation. And furthermore, if the image of A under this mapping phi sub GH is B, then if you restrict phi sub GH to the entire H class of A, it's actually a bijection onto the H class of B. In the case where the H classes are groups, which happens if and only if they contain idempotence, then this is actually not just a bijection of sets, it's an isomorphism of groups. Now, the fact that group H classes sitting inside a D class are isomorphic is a classical result of semigroup theory that goes way, way back to the origins of the subject. But this actually explicitly connects this notion with natural conjugacy. Okay. So what about the composition? Well, that doesn't quite work the way that one would want. So we always have that if you compose two of these things, so this is assuming that, you know, the compositions line up correctly on the domains and ranges of these maps. We always have an inclusion, but that doesn't have to be an inequality. So this is unlike the case of inverse semigroups where we were using these particular local sub-semigroups as the domains and ranges. So what we do is we define N of S to be not the set of all these mappings phi, but rather the monoid that they generate. This is the partial interautomorphism monoid of the semigroup. That's I'm not making an assertion here. That's a definition. And since it consists of partial bijections, this is in fact an inverse subsemigroup of the symmetric inverse monoid on the semigroup. So just to highlight what's going on here, we've started with an arbitrary semigroup which has no special, may have no special structure other than just being a semigroup, and we have associated to it an inverse semigroup of partial interautomorphisms on mapping subsemigroups to other subsemigroups. I will say that that's as far as we know anything about this. It's an interesting project just to mention some of the things here that one could make connections with. I should have listed more of these on the slide. It's an interesting project, first of all, to study the relationship between semigroups and their partial interautomorphism monoids. Of course, this would be an analog, or maybe generalization if you prefer, of looking at the relationship between the interautomorphism group of a group and the group itself. Another thing, I'm seeing in the chat, are you still seeing my slides or are you seeing something else?
I see your slide.
So do I.
Okay. Good. I was afraid something had happened there. I'll just mention one other connection here, which is getting back to the dynamical systems thing. And I've raised this with one of my colleagues who's a dynamical systems person who works on subshifts of finite type. It would be interesting to know if for natural conjugacy, there is, which is a stronger notion than the other ones that are of interest in dynamical systems. It would be interesting to know if it has a dynamical systems interpretation. That is, if there's something that about them that can, something about them that's reflected in the conjugacy of these non-negative integer matrices. Okay, but I think I'll just go ahead. I see I'm managed to hit just about the right amount of time, so I'll go ahead and stop right here.
Thank you, Michael.